I think those homework problems were very similar to the ones we did in the notes. We feel pretty good about them. All right. All right, let's finish up today's notes. We're going to do a little bit of 13-2 today. The goal is to get through enough of this today that tomorrow is a short lesson with no homework. That's my goal for you. All right, so if we can put in a little bit more work today, we'll get through enough. Hopefully we won't have any homework tomorrow. Question? 13, the dependent and independent. Day 2. Find the probability of drawing a red card, replacing it, and then drawing a black card. We've actually done this together, haven't we? All right. Let's call A, probability of drawing a red card. B, black card. Question. Are these independent events? Yes. Since they're independent, we're going to do P of A times P of B. So, probability of drawing a red. Refresher from yesterday. How many cards are in a deck? 52. Half of them are red. How many reds are there? Half of 52? 26. So 26 out of 52 times 26 out of 52 is the actual numbers, but you don't want to multiply those. You don't want to multiply those. Those are big numbers. We know both of them are a half, right? A half and a half. So go ahead and multiply 1/2 times 1/2, and we get 1/4. Put that into a sentence, please. Who's willing to raise their hand and say the probability that you put this whole story into a complete sentence? Paige.
The probability that you draw a red card and put it back in the deck, then draw a black card is 1/4.
Very good. Very good. And you notice she had to say put it back. Because what happens if you take that red card, you draw a red card, pull it out. Now how many cards are in the deck if you don't put it back? 51. And so there would still be 26 black cards, but out of 51. So they're going to have to tell us it's called with replacement or without replacement. This is if you replace it. So you're back to 52 cards.
What do you do? Do you still multiply them because they're redundant?
Great question. We're going to talk about that today. All right. Find the probability of drawing a red card, replacing it, and then drawing a 10. First of all, are these independent events?
Yes.
Because we're replacing it. Jared, how did you word that again? It doesn't affect the other. So what if we drew out a red card and didn't replace it?
There'd be more than the other. So
Doesn't that affect the probability of drawing a 10?
Yeah.
Because what if you drew a red card and it was a 10 of hearts or a 10 of diamonds that's a red card? Doesn't that affect the probability of that second draw? Do you need me to say that again, or does that make sense? It affects it, doesn't it? Okay? Flipping a coin and rolling a die, it doesn't affect the other. It doesn't affect the other at all. All right? So probability of drawing a red card, 1/2. Probability of drawing a 10. How many 10s are in the deck?
4.
Yeah, there's the 10 of clubs, 10 of spades, 10 of diamonds, 10 of hearts. There's 4 out of 52. Now, could we have reduced that? Yeah, 4 out of 52 is 1/13, right? You could reduce it if you want to, or you could just type it in and then reduce it at the end. Your calculator will do that for you. All right, so 4 over, what's that? 104? 1 over 26. So 1/26 is the chance that happens, that you draw a red card, put it back, and then draw a 10. That's not very likely, right? We talked about being likely is about 75% and above. We know 50% is like, they use the expression like a coin flip, all right, for a reason. 1 out of 26, not very likely. All right, let's do this one. Flipping a tail, then rolling a 5, pulling a multiple of 4 out of a hat with the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. All right, how many events are there? 3. Let's do it one by one. Event 1, flipping a tail, probability, 1/2. Event 2, rolling a 5, 1/6. And I kind of got ahead of myself. Are these 3 events independent? Yes. Event 3, pulling a multiple of 4 out of a hat with those numbers in it. How many multiples of 4 are there? What are multiples of 4?
There's 4 numbers.
4, 8, 12, 16, 20. Ooh, this is fun. 24. No, let's stop.
So we're not using all the
So how many multiples of 4 are there? 4, 8. So what are the chances that you draw a 4 or an 8 out of that hat? 2 out of 9. All right, let's go ahead and multiply these and see what we get. 2 out of 108 or 1 out of 54? 12, 90, 18, 108. Is it 1 out of 54? Double check me. And if you read it as a decimal, or percent, that's fine. What'd you get? Should be a little over 2%, right? What'd you get, Jared?
I got 1.8 or 0.18.
Oh, so it's a little under 2%. Okay. 0.18 or 18% chance. So these are all ways we're going to write probabilities. Fraction, 1 out of 54. Decimal, 0.18. Percent, 18%. Press time.
I got 0.0. Yeah, I forgot to say.
Oh.
It's 1.8.
All right, Jared, let's do this again. Yeah, it should be 1. Here's what I said, a little bit more than 2. Well, a little less. Hold on a second. 1 out of 54 would be 2 out of 108. 2 out of 100 would be 2%, right? So it's about 2%. What is it again? 1.8?
0.01.
So 1.8%. Okay, remember, move it over 2 places to get it as a percent. 1.8%. Make sense? On to dependent events. In a deck of cards, find the probability of drawing a 7. Do not replace it. Then drawing another 7. Okay? So we've got our deck of cards. Drawing a 7. Do not replace it. And then drawing another 7. Oh, I lost it. I had my deck of cards out earlier. All right. I think we can do this. First of all, do you guys agree these are dependent events? And how would you word that in this case? Someone else. Olivia?
They took one of the 7, so it would only be 3 and 4 of the rest of them.
Yeah. Yeah, it definitely affected that second draw, didn't it? So what is the probability of the first event happening? 4 out of 52, correct? 4 out of 52 times. Now, here's the problem. We didn't replace it. There's not 52 cards anymore. Now there's 51. And what's the probability of drawing another 7? Well, how many 7s are there now? 3. So this is our multiplication rule for dependent events. Okay? There's going to be a couple ways we think of it. For today, we're just going to say what's the probability of the first thing happening? Okay, now what's the probability of the second thing happening, knowing that the first event changed the probability for the second event? Okay? So here we go. 4 times 3? 12 out of 52 times 51? 2,652. Is that what you got? All right. I'll be asking you the decimal for days, though I don't do it myself. All right. 12 over 2,652. All right, 0.0045. 0.0045. Or 2 decimals over, about 0.45%. So less than a half of a percent chance that you do that event of drawing a 7, not putting it back, and then drawing another 7. Very unlikely. All right, I want you guys to try the next one.
She said, how would you subtract 4 from 52 to get the not spade? 13.
So how many spades are there? There's 13 spades, 13 clubs, 13 hearts, right?
Mm-hmm.
So yeah, 52 minus 13 will tell you how many not spades there are.
It's like 30 something.
All right, first drawing of a card. How many not spades are there? 39 out of 52, correct? And again, there's different versions of these fractions. I'm just doing the raw numbers, so you're like, oh yeah, there's 52 cards and there were 13 spades. Then there's 39 non-spades, right? Now, what's the probability of the second draw? Well, we're drawing a spade. How many spades are in there? 13. Do you guys agree? 13? 13 spades.
Yes.
Not getting much feedback. Thank you for those who did. Out of 51, because we didn't replace the card, right? 13 times 13 out of 51. Again, I think what's like this, some of this stuff might not be obvious to some of you, and that's okay. All right, but the more you see it, like, oh, okay, I see why you did that now. We didn't draw a spade on the first one, right? It was a non-spade, so there's still those spades in the second drawing, but there's one less card because we drew maybe a diamond, maybe we drew a heart, maybe we drew a club, right? So there's one less card in the deck, but there were still 13 spades. All right, so we got 39 times 13, 507, over 52 times 51. Was that the 2,652? .191, about 0.191, or 19.1%. Tough.
Why couldn't we write 3 over 4 for the probability of not drawing a spade?
Is 39 out of 52 3/4?
But wouldn't that change the multiplication answer in the end?
No, it'll just give you a more reduced form of that number. Yeah. All right. Questions on that? All right, let's go to this last example, and then we'll get a little bit into the next section. A bag contains 21 $1 bills. How many $1 bills? 20. 5 $10 bills. So how many bills are in the bag? 25. Good. you randomly draw a bill from the bag, set it aside, then randomly draw another bill from the bag. Find the probability that both events A and B will occur. All right, so event A is drawing a $10 bill. Okay, first draw. And event B is drawing a $10 bill on the second draw. Let's vote. Independent or dependent? Who votes independent? Who votes dependent? For sure, right? Because you draw a $10 bill, and what do you do with it? Set it aside. Okay, you've taken it out. You have not replaced it. That definitely affects the second drawing. So what's the probability of event A happening? 5 out of, you say 25? What's the probability of event B happening?
4 and 24.
Yeah, now there's only 4 $10 bills out of 24, and we're going to multiply these together. So we get 20 out of 600. What was it, Olivia? 0.33?
Yeah, no.
0.033?
0.033.
Yeah. It's going to be repeating. So about a 3.3% chance. All right. Here's another one. This stuff is used all the time, okay? And just a quick little application. How many basketball players in here? Basketball players? So, what's a typical average free throw shooter in high school? Like, what's the percentage?
Somewhere around like
75%? Okay. So, they walk up to the line. There's a 75% chance they're going to make it, right? What are the chances they go up to the line for 2 shots and they miss both? End of the game, you got to make one. What are the chances they walk up to the line and miss both if they're a 75% free throw shooter across the season? It's 25% that they miss the first one, right? So 25% is a fourth. So that they miss it, correct? Times, now are these independent or dependent? Independent. If they are, now we're not going to get into the psychology of it. Oh, I missed the first one. And it gets into your mind. We're not going to talk about that. All right, take that out of the equation. If their probability is 75%, okay, they got ice water running through their veins. That's not healthy. Don't do that. Then there's also another 1 out of 4 chance they miss the second one. So 1/16 that they miss both. So a 6.25% chance they would miss both. All right. So it's kind of an interesting application. You play the numbers and a lot of analytics. Probably if you watch sports at all, there's a ton of talk about analytics in sports nowadays. This is the kind of stuff they do, going for 4th down on wherever yard, field position and distance. That's for tomorrow. All right, conditionals and two-way tables today. Again, we're just going to get into the lesson a little bit. Nothing too crazy. My goal is that you have most of the class period tomorrow to work on it.
It was real funny. Like, it was real hot during
Right. What do you draw for our?
I can't stand changing my though.
Yeah.
Like every few months I'll rearrange.
And then what did you draw for him?
All right. We're going to learn some new notation today as well. All right. Now, we've already done some of this already. Like it's kind of hard to avoid doing one thing after another without learning what's called the multiplication rule. We just practiced the multiplication rule quite a bit. All right. This is red. This is an and. Okay. We're gonna learn new symbols today. This is an and. This is an or. Not the kind you paddle with. Tough crowd. All right. What does this look like to you? How would this be easy to remember that that's an and?
There's an
It kind of looks like an N. And this one doesn't. Right? That's the way to remember it. And or. All right. The probability of the intersection of A and B, there's an extra and in there, means what is the probability that both A and B will happen? All right. So when you see this, you have A and B. What's the probability that both? We read and as both. All right. We learn that to find the intersection of two events, we multiply the probability of each event. Tell.
Is there a way to draw them to make them look less like N than U's?
No, they're supposed to look like that. Is that what you're asking?
Yeah.
Yeah. All right. Do you agree the intersection means both? Like if I say, hey, let's hang out after school today. You're like, please no. I say, I'll meet you at the intersection of Market and 619. What is sheets, Ryan? No, actually we're not. We're living dangerously because if I say I'm going to meet you at Market and 619, and you take it literally, where would you be standing? Under the traffic light on Market and 619, right? Like intersection literally means the intersection, like where those streets cross. You're both. I don't know if you've ever stopped and thought about it. It's kind of weird. I'm on both Market and 619. I'm on two streets at once, right? If you're on the intersection, that's what I want you to be thinking when you read and. All right. This is read as or. Probably that either A or B will happen.
Where's the writing for this?
Did you write that down for and?
No.
And.
What are you writing down?
The equation.
Oh.
Yeah, P of A times P of B.
Isn't that what we've been doing?
It's similar. The difference here is going to be the or. Here's the or. Now, here's the confusing thing. All right, I need you to listen carefully. To find the probability of the intersection of two events, we need to know if the events are what's called mutually exclusive. Okay, and I'm going to use that road analogy a couple times today. Are Market and 619 mutually exclusive? No, they're not. They cross. They share space. Are hearts and kings in a deck of cards mutually exclusive? No, they share the... Are hearts and kings mutually exclusive? No, they share the king of hearts. They share the king of hearts, correct?
Is or like the dependent of...
Not quite. Because what if I say, what's the probability that I roll a 3 or flip a head? Are those mutually exclusive?
No.
Roll a 3. Flip a head. Are those mutually exclusive events? Is there any overlap? No, those are mutually exclusive events. Back to a deck of cards. Are 4s and red cards mutually exclusive? No. There's the 4 of hearts and there's the 4 of diamonds. Are red cards and black cards mutually exclusive? Yes. Okay. So these are two events that cannot occur at the same time if they're mutually exclusive. Now, not mutually exclusive. In a deck of cards, a 2 and a spade. On a die, an odd and a 5. Those are examples of not mutually exclusive. All right? So, here is your OR probability. P of, this is very important that you know this. A or B. It's P of A plus P of B minus P of A and B. Sounds confusing? Not that bad.
Doesn't matter which one you do first. Oh wait, are you multiplying the A and B?
P of A times P of B, yes. P of A and B is P of A times P of B. Now,
Wait, so the second part is multiplying the A and B.
it's the overlap of A and B. It's P of A and B.
So we are multiplying.
We'll talk about that in a minute. Okay. I want to give a couple of visual examples. I think most people, once you see it, it's gonna be like, that makes sense. Get that down? All right. I'm going to get to that in just a minute. I want to give you a visual example first. Here's a section of Route 619. Or East Maple Street. East Maple? West Maple? West Maple? Which one is it here? West Maple Street? Here's Market. For those of you who are getting hungry, here's Sheets. Aldi, gas station, anger room. What do they call it? Rage room. Rage room. All right. You guys remember the AirPod example from yesterday? Oh, I lost my AirPods on the way home from school.
Oh yeah.
Okay. Do you remember how we added the length of the road and found out how far we traveled total?
Yeah.
Right? And then we took the one street, the length on that street over the total and found out the probability it was on that street. Yeah. Yep. So, that was a homework problem. I kind of want you thinking about that, but let's do a different example today. Let's say a road crew is going to pave these roads, okay? Potholes are getting bad. They're going to pave the roads. Tell me what's wrong with their calculation. They go through, they pave 619, they're doing the calculations. They haven't even gone out there. They're the county engineer is working on the calculations. And they're like, oh, these are rectangles. I'm going to find the area of this section of 619. All right. And then they're like, okay, we're also going to pave this stretch of Market. Let's find the area of that section of Market. Isn't that satisfying? I love how it turns green. All right, they calculated the amount of road to pave in yellow. They calculated the amount of road to pave in blue. And they take yellow area plus blue area. And they send it out to the road crew. Here's how much asphalt you need. It's a problem. Paige. Go for it. You raised your hand. You earned it.
Well, they're gonna overpay the green section.
Yeah. What should they do with their calculation?
Subtract that.
Subtract off the green. How many of the green? Just one. Because you counted it with yellow. You counted it with blue. You only should have counted it one of those times. So how would you word that? Take off the where it's both yellow and blue. You see how you're taking away the overlap? That's your formula. One plus the other minus the overlap. Because market and 619 are not mutually exclusive.
So are you finding the area of that little circle?
Yeah. Now this is just a visual example that I want you guys to get to see why the formula works. Okay? Does that make sense visually? Now it's also going to make sense in a probability sense. Okay? All right. Let's do a couple of these examples. What's the symbol again? And or? Or. It's not an and. It's an or. All right. So what's our formula? Probability of rolling a 2 plus the probability of rolling a 4 minus the probability of rolling a 2 and a 4. Wait a second. What's wrong with that? There's never a time when you roll one die that's going to pop up as both a 2 and a 4. Do you agree? Because these are mutually exclusive. This is not necessary on this example. So here's what you're going to do. If the events are mutually exclusive, all you need to do is add the probability of the first and second happening. What is the probability of rolling a 2? 1 out of 6. Now be careful. Or we are adding. What's the probability of a 4? When you add them, you get 2 out of 6. Okay, or 1/3. Does that make sense? So what does that mean? Let's give an example to this. I roll the die. I'm not rolling it twice, am I? You see how this is one event? And it's either going to pop up as a 2 or a 4. Oh, that makes sense. Those are 2 possibilities out of 6, aren't they? 2 out of 6. 1/3. Does this make sense? This is not 2 rolls. What if I said you roll a 2 and then you roll a 4? Multiply. Or add. Right? Last one for today. A P of 3 or an odd number. Well, what's the probability of a 3? Plus P of odd minus P of 3 and odd. Well, what's P of 3? You said it? 1/6. What's the probability of an odd? Let's write 3/6. Okay, I know it's a half, but let's write 3/6 just so you can see what's going on here. Minus, what's the one we accidentally counted twice?
3.
The 3, because it's a 3 and it's an odd, right? Minus the overlap. So what's our answer? 36. Or 1/2. All right, we're going to continue with this. It could get a little tricky. I understand that. All right, we will do a little bit for both sections. The 3 is an odd number. So 1, 3, and 5. The 3 is it's a 3 and it's an odd number.
But I thought you multiplied the 1/6 and the 3/6.
It's the overlap.
Is there a form of racism towards voters?
I didn't get any of that. Numbers don't have it.
It'll be specious.
That's not right.
Yes, you are. There's only like a few that you actually
Dude, I drew the world's derpiest. It's amazing. It looks like it would belong in like an old Flash game.
Oh,
I'll tell you what, guys. I'm just gonna have you do 13, 14, 15, and 16. I'm not gonna assign anything new from the or probability from today. All right, just do those problems. We'll try to get most of it in class tomorrow.
This is really cool. No, that's not my question.